Okay, so what you should have finished today in class is we should have gotten to the fill this in. Okay, I filled in the dark blue stuff in class. Wanted you to go back and fill in the light blue stuff from what we did above. So if you haven't gotten that done, do that now. I told you yesterday that you were going to have to pick up something on the way in because I was going to have an additional part to this. I changed my mind. I decided I wanted to just finish these notes, let you work a little bit in class today with the time that you have left, and then I would rather do the next part with you together. I think that would be better for me to do it in person than in a video. So let's look at example 4 here. Actually, before we do that, let's look at these identities again. I want to look at the patterns again. So I have sum and difference identities. This is the sums. These are the differences, right? And so we see that sine is the two trig functions change. It's like a sine times cosine, not sine times sine. So since the trig expressions change, the sine does not. With cosine, the trig expressions stay the same when we multiply, so the sign does change, okay? And that works for the difference identities as well. Also, between the sum and the difference for each one, notice that the terms, these two terms and these two terms are the same. What changes is the sign. Same thing here with cosine, okay? Then we have double angle identities, and we came up with a few other ones for cosine of 2 alpha that you can figure out with substitution if you need them, okay? So let's look and see how we're going to use this. It says, which of the following is equivalent to the expression 2 sine of pi 14ths times cosine of pi 14ths? Now, pi 14ths is not an angle you know. Neither is pi 7ths or pi 28ths. That is done on purpose because you can't just evaluate these and see if the answers match. You have to know how these identities work. So you need to see if I have these, can I simplify this? Can I change it? Or do I have something that looks like this? I know that I have an identity that says 2 sine alpha times cosine alpha. And that is equal to sine of 2 alpha. It comes from this right here. And here's the pattern, 2 sine alpha cosine alpha. Alpha would be pi 14ths. So if this is equal to sine of 2 alpha, then this would be equal to the sine of 2 times pi 14ths. And then when I multiply that, that gives me the sine of pi 7ths, which is C. Okay? Before we go to the other side, we are going to look at this. This is the reference chart I told you about yesterday. It's what I have used in the past for a reference sheet when we did identities. We did not do every single one of these identities. We did the identities up to here, okay, up to the power reducing. And sometimes we got this far and sometimes we just stopped here. But I want you to see it overall. I'm going to make it where we can see it better. And we're going to see what we can actually eliminate from this, what we don't have to know for the AP exam. Okay, so one thing we do need to know the reciprocal identities and the quotient identities, which we talked about yesterday, and we totally already know. Then we learned the Pythagorean identities. And remember, there's even different forms of those, but that's where they are. And these are actually written with the +1 in the second location each time, but we had them different because we actually created it from here. They can be written different ways on different formula charts. Now, the cofunction identities and the even odd identities, we can actually come up with these by using the difference identities that we know, but we're not using cofunctions, so I'm going to mark those out. That's something we don't have to know. Even odd identities, also not part of AP. Okay. Then we do have the sum and difference. Okay. Sum and difference. But we only have to know for sine and cosine. We don't have to know them for tangents, so it eliminates that. Then yesterday we did come up with our double angle identities from our sum and difference. Here's our sine of 2 theta, and here's cosine, all 3 versions, but we do not have to know tangent. And then we get up to here, And we don't need to know half angle or power reducing, so I'm going to mark those out. Okay. And then we also are not doing product to sum or sum to product. So when you feel like this is overwhelming, there's a whole lot more that they could make you have to know, and you don't have to. So I'm going to highlight these because I'm actually going to refer back to this some just because it's going to be easier for me to point to it on here than it is for me to flip back through the notes when I just don't want to write it all down, but I want to refer to something. And I might make a cleaner version, but I'm not going to use it a ton. So. And then, again, I'll show you this. So you can see overall the things I highlighted. Those are the things we have to know. The things that are marked out, we don't have to know. Okay? But you will realize you already know that top row. The Pythagorean identities are no big deal. And once you start actually using these and you see the patterns and you're more comfortable with them, it's really not that bad. You just have to not, think negatively about it the whole time. Okay. So with that said, let's go back over here. Let's go to the next page, or the back of that. All right, so the function k is given by this function right, oh my goodness, never fails. This right here, which of the following is an equivalent form for k of x? Okay, so I have cosine of 2x. Now, one of the things you might know, like the one that kind of usually will pop into my head for that, I know that I can write cosine of 2x equals cosine squared x minus sine squared x. Now, before I worry about figuring any of this out, not a single one of these has cosine squared minus sine squared. This one has cosine squared plus sine squared, but that's the Pythagorean identity. That's not it, okay? Or at least that doesn't match this exactly. So when I look back over here, I have these other options for my double angles. And if you can remember this one, these two really aren't that bad because it's still minus, but if the cosine squared is going to become 1, then I get 2 of these. If the sine squared is going to become 1, then I get 2 of those. Okay, it's just, again, once you work with them some, you kind of get the hang of them. And when you actually write them down more and more, that helps as well. So when I'm here, I can say, okay, that's one version, or I can have 1 minus 2 sine squared x, or I can have 2 cosine squared x minus 1. Like all three of these are viable candidates. Now, this is 4 times the cosine of 2x, so I'd have to multiply each one of those by 4. So I could have 4 times cosine squared x minus sine squared x. Well, without doing anything else, I can tell that if I do that, it comes close to this, but it's not positive. Okay, so that's definitely not the one I want to use. Or I'm going to have 4 times, well, guess what? These have them multiplied. That doesn't make any sense, so I don't like that one. This has it added. I don't like that one. So these, I don't even have to try this one because these both have cosine in it. So if I multiply it by that, then that gives me 8 cosine squared x minus 4. And my answer is C. Okay. Equivalent forms, right? Okay, so now I have this. I have cosine of 8, or pi over 8, cosine of pi over 16, minus sine times sine. So here's what I know. I know that if these don't change, that's cosine. So this is going to be cosine of either a plus b, so of either pi 8ths plus pi 16ths or pi 8 minus pi 16ths. Then I remember that if these two don't change, this sign does, so this should be plus. Then I have to know how to do fractions. So this is going to give me the cosine of, this would be 2 pi over 16 plus pi over 16, which is going to give me 3 pi over 16, which is D. If I had added these two, and I had gotten sine of pi thirds, then I probably would need to also evaluate that. But since it's 3 pi 16ths, that's not one that you know, and that's totally fine. Okay? All right, so let's look at example 7 here. All right, so it says the figure shows a circle centered at the origin with an angle measure of theta. So here's my theta in standard position. The terminal ray of the angle intersects at point P. Okay. The coordinates of point P are 5, 12, and I want the value of the sine of 2 theta. Okay, well, I know that this is x, this is y. Well, I didn't really need to put x there. X, which is 5. This is y, which is 12. I can find the hypotenuse by doing Pythagorean theorem or by paying attention to what's in front of my face, because this point is at 13, 0. That is the radius, so that makes this right here 13, which I would also get from the Pythagorean theorem. So then I want the sine of 2 theta. So I know that the sine of 2 theta is equal to 2 sine theta cosine theta. So that means I get 2 times, all right, so the sine of theta, sine is y over r, so that's 12 over 13, times cosine theta, which is x over r, which is 5 over 13. Then I need to multiply all that together, but I'm going to work smarter, not harder. So 2 over 1, right? Multiplying fractions is easy. I'm going to multiply all the way across. So let's do the denominator first. 13 times 13 is 169. That's a perfect square. That's something you should know. Now, I could multiply 2 times 12 and get 24 and do 24 times 5, and there's absolutely nothing wrong with that. But if I multiply 2 times 5, I get 10. That's way easier to multiply, and 10 times 12 is 120. And that is my answer. Okay. All right. So let's look at these. Figure shows 2 circles centered at the origin with the angle measures of alpha and beta. So this is alpha, this is beta. In standard position, the terminal ray of alpha intersects at point P, and terminal ray of angle B intersects at point Q. Okay, we've got our little ordered pairs there, so I'm going to draw in this triangle. So this means I know that this is -5, this is the square root of 11, and this is 6. I'm going to draw this in. You always draw it to the x-axis. This is 2. This is the square root of 5. The radius is 3. Okay. So I want cosine of 2 alpha, I want sine of alpha plus beta, and I want cosine of alpha minus beta, which tells me I'm going to need sine and cosine for each one of these. So I'm going to go ahead and find those over here. And I'm going to say, all right, I know that cosine of alpha, that is going to be x over r, so that's -5 over 6. And then sine of alpha is going to be y over r, square root of 11 over 6. I'm going to come over here, cosine of beta, that is x over r, that is 2/3. And sine of beta is going to give me y over r, that's the square root of 5 over 3. Okie dokie. So here, I want the cosine of 2 alpha, okay? No need to get fancy. The one that probably sticks in your head the best is that cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. Sorry, I didn't need those parentheses, but it threw me off. Parentheses are fine there. Sometimes it's a bit much. Okay. So that means that this is going to give me, so cosine of alpha is negative 5/6. But I got to square it. Minus sine of alpha, which is square root of 11 over 6, and that gets squared as well. So then that's going to give me 25 over 36 minus 11 over 36, which is 14 over 36, which is 7 over 18. And that's my answer. Okay. Then I need to do sine of alpha plus beta. Okay, sine of alpha plus beta. When I do the sine, I start with sine of alpha, and it changes cosine of beta, cosine of beta. These change, so the sine doesn't, and then I have cosine of alpha, sine of beta. Right, then I substitute it in. Sine of alpha, square root of 11 over 6, times cosine of beta, 2/3, plus cosine of alpha, which is negative 5/6, times sine of beta, which is the square root of 5 over 3. So then this is going to give me 2 square roots of 11 over 18, and then actually that could be, I can make that minus 5 square roots of 5 over 18. And then I could leave it like that, or I could clean it up a little bit and say that that is, well, let me do it underneath there. That is 2 square roots of 11 minus 5 square roots of 5 all over 18. But really stopping here would be fine too. All right, so then I have cosine of alpha minus beta. So that's cosine of alpha, and cosine goes cosine, cosine, times cosine of beta. These did not change, so the sign does. Cosine, no. That should be sine of alpha, sine of beta. Okay, so then I substitute it in. Scroll back up so I can see. Cosine of alpha is negative 5/6 times cosine of beta, which is 2/3, plus sine of alpha, which is the square root of 11 over 6, times the sine of beta, which is the square root of 5 over 3. So then this gives me negative 10 over 18 plus the square root of 55 over 18, which again, I could leave like that, or I could clean up and say it's negative 10 plus the square root of 55. That's, oh my gosh, 55 over 18. Okay, so here's what I want you to do. I want you to work on that assignment, work with each other, and be prepared to ask me questions tomorrow. Okay? Ask me questions about the notes after you've processed it some. Let's go back and say, hey, can you look at this again or whatever, because we need to move forward from here. All right, see you tomorrow.